Yeah, Kanapura.
Got got it, sir.
Okay, very good. So Benazira, I sent you an applied soil mechanics tutorial. So please open it. Check your email.
Yes, sir.
Oh. Yeah. So good morning to everyone. So since a couple of the classes we were discussing about the different theory, stress path, Mohr circle, so on and so forth. So though we discussed elaborately the theory behind all these fundamental concepts, but we were not taking care of any tutorials on the same aspect. So let us dedicate a couple of the classes to enrich our knowledge on the shear strength theory, stress path, and measurement of the calculation of the core pressure parameters, so on and so forth. I have already forwarded the tutorial on applied soil mechanics to your email. Kindly check and open it and start solving all the problems. So wherever you are facing a problem, so then I will intervene. So then I will try to give you a solution. So if you look at the
Sir,
yeah,
sir, after completing all the question, we have to submit, sir.
no, you don't need to submit it. This is not assignment.
Sir,
This is tutorial.
sir, this is just for practice, sir.
Yes.
Okay, sir. Thank you.
So let us open the very first problem. So here a soil element has been shown, so which is subjected to both axial and lateral stress as well as the shear stress. So if you look at carefully, so on this element, a 100 kPa in the vertical direction and 40 kPa in the lateral direction, uh, and a shear stress of 20 kilopascals both in the clockwise and anti-clockwise are acting. So here, if you look at this element carefully, so as the shear stress is acting on the element, so therefore, so it should be clear to you by now that this element is not subjecting to the principal stresses. Is it clear? So as the element is subjected to the shear stress, so the applied 100 kilopascals in the axial direction and 40 kilopascals in the lateral direction are no more a principal stress components. Rather, you can designate them as sigma x and sigma y. Now, you need to draw a Mohr circle to determine the given points, the magnitude of the major and minor principal stress, the stresses on a plane inclined at 25 degree to the horizontal, and the maximum shear stress and the plane on which it acts. Okay. So how do you go about this one? So even if you look at the element in the axial direction, so they are compressing the soil element, while in the lateral direction, so they are expanding the soil element. Okay, so the stresses in the axial and the lateral direction are in opposite direction. Similarly, so the stresses or the shear stress on the horizontal plane is in an anti-clockwise direction, while the shear stress on the vertical planes is in the clockwise direction. So you can presume anything. So depending upon your easiness, so clockwise positive or anti-clockwise negative or vice versa. So depending upon your convenience. So here what I'm assuming is compression as a positive, tension as a negative, clockwise shear stress as a negative, and anti-clockwise shear stress as a positive. So if I do so, then the stresses acting on the horizontal element, which are 100, 20.
Ah,
So stresses acting on horizontal element are 100, 20. So these are the stresses acting on the horizontal element.
sure, I have understand. Sure, I have understand.
Yeah, can you mute yourself? Okay. So this is the point of stresses. If we convert this into coordinates form, the first point is 100, 20. So since 100 is in the compression direction, so therefore it is positive. And 20, so this is in the anti-clockwise direction, therefore it is positive. While on the vertical axis, the lateral stress acts in the expansion direction, so therefore it is minus 40. So therefore it is minus 40. Similarly, the shear stress acts in the clockwise direction, so therefore it is also a negative, that is minus 20. So minus 40, minus 20. So these are the two coordinates that you can able to derive, so based on the given stresses acting on the soil element. So depending upon the coordinate system, so that you assume, so you try to identify these 2 points. So here I am approximately taking, so this as a positive, this is the first point. So 100, 100, so 20. 100, 20. While the other coordinate system is negative and negative, so I can take, so minus 40 and minus 20. So this is minus 40 and minus 20. So these are the 2 points. Okay, ideally, so this is 1 point, this is another point. The distance between these 2 points will be equal to the diameter of the Mohr circle. So this you can treat it as diameter of the Mohr circle. So this is the diameter of the Mohr circle. Okay, so this means the normal stress axis at some point. You can designate this as a center of the circle. Center of the circle. Now I know the diameter of the Mohr circle, and where it is intersecting the normal axis, that is the center of the Mohr circle. So with C as the center, any one side as a radius, so you can able to draw the complete Mohr circle. So this is how you can able to construct the Mohr circle. Now wherever this circle is touching the normal axis, so that would yield the maximum and minimum principal stress, that is sigma 1 and sigma 3. So this you need to do it in a graphical way. Okay, so this you need to do it in a graphical way. However, wherever the Mohr circle touching the tau axis, that will not be equal to, so the shear stress. So the shear stress that you need to draw, so that corresponding to always at the center. Corresponding to always at the center. So here if I redraw a little bit carefully. So somewhere here, this is tau max. So that is the maximum shear stress. So this is the horizon. So this is the horizon. So maximum principal stress sigma 1. So maximum, so major principal stress and the minor principal stress. So that is sigma 1 and sigma 3. Now what has been asked? So the magnitudes of the major and minor principal stresses. So this now we could able to determine when you draw it on a graph sheet. Similarly, identify the topmost point. So that would give you the maximum shear strength or the maximum shear stress that is acting on the element. Now, in a next step, so you are asked to determine the stresses on a plane inclined at 25 degree to the horizontal. So this is the most important point. So since the stresses given are in the form of a sigma x, sigma y and the shear stresses, so it is important to identify the pole point. So as I explained in the previous class, in order to determine or identify the pole point, what you need to do, you have to take a drafter. So keep it parallel to the horizontal axis. Keep it parallel to the horizontal axis. And here say I am designating the first point as A and the second point as a B. Second point as a B. Now A as a reference point. A as a reference point. The element horizontal surface as another reference point. So from the A, so draw an horizontal line. Draw an horizontal line. So wherever this horizontal line touches the Mohr circle, so that is one point. Similarly, so your vertical axis, the vertical surface as the reference axis. So B as the reference point. Draw another line. Wherever these 2 points will meet, that point is called as a pole point. That point is called as a pole point. So here, so if you draw the horizontal line with reference to the horizontal plane, vertical line with reference to the vertical plane of the element, so these two will meet at P. That is called as a pole point. Okay, so now P, the pole point as a reference point, you need to draw an inclined line 25 degree to the horizontal. 25 degree to the horizontal. So this as a reference line, draw an horizontal line, So this meets the Mohr circle somewhere here. So this is the 25 degree. So this is called as the normal stress sigma ff or tau ff. So those are acting on the inclined plane, which makes an inclination of 25 degree with respect to the horizontal. So this is what you need to determine. Of course, you can also determine same thing by analytical way, so that you can do it. So there is no problem, but this is the graphical way. So these are the stresses. So in a sense, if you draw the free body diagram of an element, so this is the element. So it is subjected to 100. So this is also, so this is 100 and this is 40. So this is also 40 and this is shear stress. So this is 20 shear stress. So now you draw a plane. So this is plane, say XX, plane XX. So this is plane XX. So which makes an inclination of 25 degree. So you are asked to determine, so because of this combination of the load, what are the sigma F, and what are the tau F. So these are the stresses that you need to determine. So graphically. Okay. So next, the maximum shear stress and the plane on which it acts. So here the maximum shear stress is right on the top of the center of the Mohr circle, that is tau max. And tau max can also be determined in another way. So tau max can be represented as the radius of the circle. So that is sigma 1 minus sigma 3 by 2. So sigma 1, that is major principal stress, which is the intercept on the extreme right side of normal axis. Sigma 3, which is again the intercept of the normal axis on the left side. So when you draw this in a graphical way, you could able to determine sigma 1 and sigma 3. So substitute here. So then what you get is tau max. Now suppose if somebody is asking what is the angle made by the failure plane with respect to the maximum shear stress. With respect to maximum shear stress. So the maximum shear stress is this point. With respect to pole as a pole as a reference point, you can draw another line. So this will become the angle made by the, so this is alpha. So alpha means the angle made by the failure plane at maximum shear stress condition. At maximum shear stress condition. Okay, I hope this is clear to everyone. If anybody has any question, so feel free to ask me. So it's very simple and straightforward.
Sir,
So yeah.
sir, kindly mention answer so that whenever we complete, sir, we can make clear, sir.
No, you try to do it right now. You can do it analytically also. So the answer is sigma 1 is 104. Just check it. This is 104, and sigma 3 is minus 42. So this is minus 42. The maximum tau max is 73. So this is 73 kilopascal. And normal and shear stresses are I think given sigma 1 minus sigma 3 by 2. Yeah, 61 and 66. So these are 61 and 66. So please note down. So this is the answer.
And the last question they ask about on which plane maximum shear stress is lying, sir.
Yeah. So suppose if you want to measure, you can measure this. That is alpha. That is an additional thing I told you.
So can we measure alpha by an analytical method?
Yeah, you can do it. You have to take some geometrical identicality. Take the geometrical identicality, then you can solve it. You can still do it, no problem. Okay, so then go to the next sum. Given the stresses on an element as shown below, find the stresses on plane XX. So here, if you look at the second sum, the stress of 20 kilopascal acting on the horizontal plane, and a stress of 50 kilopascal, it's not 40, it is 50 kilopascal, acting on the horizontal plane, sorry, on the vertical plane, So here, no shear stresses are acting on the element. So therefore, you can presume that 20 and 50 are major and minor principal stress components. Can I rub it off? Hello.
Yes, sir.
Okay, so try to solve the second one. But if you look at the second one, where is the maximum principal stress acting on x-axis, horizontal axis or the vertical axis? Which is major and which is minor?
So 50 is major and 20 is minor.
Yeah, so here major principal stress is acting on the vertical plane or in the lateral direction, and minor principal plane is acting in the horizontal plane or in the axial direction. So here it is given that others, most of you are so silent. I couldn't able to understand whether you are understanding the tutorial or not. So blindly speak up. So this is 50 kilopascal, 50 kilopascal, so 20 kilopascal and 20 kilopascal. Okay, since no shear stresses are acting on the element, we can straight away presume that this 20 and 50 are minor and major principal stresses. So minor principal stress is acting in the horizontal element, major principal stress is acting in the lateral direction. So try to draw the Mohr circle. So this is tau and this is sigma. So I don't need to re-emphasize again. No shear stresses. So therefore we can consider, so this is sigma 1 and this is sigma 3. So sigma 1 is 50 and sigma 3 is 20. So try to draw the Mohr circle. So sigma 1 and sigma 3. So find the stresses acting on the plane. So this is sigma n and tau n. So what is the maximum normal stress and the maximum shear strength that is acting on the plane axis? So now how do you identify the plane?
So the pole will be at sigma 1, and after that we will draw XX
Okay.
axis.
So why the pole is at sigma 1?
Because first we will draw a vertical line through sigma 1, because on the plane on which it X.
Yeah.
And after that we will draw horizontal line from sigma 3. It will intersect at sigma 1.
Okay. So if you draw this horizontal and vertical line, so they will intersect at sigma 1. So this will become the pole point. Okay. So this will become the pole point. So sometimes in some books you can also see that. So usually means when they are taking this concept, there are two ways. Either you can directly measure the theta. So here it is given 30 degree. 30 degree. But the stresses that you need not to get confused. Where is the major and where is the minor principal stresses are active. Okay. So now what you do is, since I know the pole point, so draw a line parallel to the plane xx, parallel to the plane xx, with pole point as a reference point, with pole point as a reference point. So draw a parallel line. So this is 30 degree. So this will represent your x plane, and wherever this plane is touching the Mohr circle, so those are the values of the sigma n and tau n. Sigma n and tau n. So the values of these two are 27.5 and minus 13. So 27.5 and minus 13. So this, suppose if you draw this Mohr circle in a graphical manner, and if you draw a plane xx which is exactly perpendicular or parallel to, perpendicular to the plane x-axis. So alternatively, so we can also determine the sigma n and tau n by analytical means. Suppose if you determine the sigma n by analytical means, what is the equation? What is the equation?
Plus sigma 2 by 2 plus sigma 1 minus sigma 2 by 2 sine 2 theta.
So sigma 1 plus sigma 3 by 2
cos 2 theta. So sigma n is cos 2 theta. Sigma 1 plus sigma 3 by 2
Cos 2
plus
theta.
yeah, sigma 1 minus sigma 3 by 2 cos 2 theta.
sigma 3 by 2 into cos 2 theta. Okay. So then what about tau n?
Sigma 1 minus sigma 3 by 2 sin 2 theta.
So sigma 1 minus sigma 2 by sine. Okay, but here suppose if we use the theta directly 30, you may not get the exact values of the 27.5 and minus 13, rather you will get a different value. Suppose if I take here theta is equal to 30 degree, where would be the failure plane? Anyone else?
Repeat.
See, suppose if I take theta is equal to 30 here, so will you get the values of 27.5 minus 13? Just check it once, because this is one of the very intricate thing that everyone has to understand.
No,
Sir,
sir,
we
it's
have to
different.
consider theta equal to 60, sir.
Theta is equal to 60. Suppose if I take theta is equal to 30 here, will that plane represent this one, or will the payload plane is different than this one?
The difference, sir. In Mohr circle, it is rule that when we draw according to 2 theta, sir.
According to yeah, it is 2 theta only. Yeah. See, 2 theta meaning is different. Suppose it.
Sir, it will come to the perpendicular to that direction. Sir, sir, it means at 120 degree it will come.
Yeah, 120. That is correct. But how? See, suppose if you take 30 here, then that might represent the failure plane something like this. It's not at the bottom. Okay, so this is not correct. Then you will get the stresses somewhere here. So these stresses and these stresses are not equal, or maybe different also. Okay, in this case you have to take theta in the anti-clockwise direction. So this angle you have to take as a theta. This is not 30 is the theta. So whenever you find the major principal stress in the horizontal direction or in the lateral direction, you have to take theta in the anti-clockwise direction. So or the another value. So that is 120. Your theta will become 120 instead of the 30. Or no, it's not 120. 60, na? 60 or 120?
Sir. 120, sir.
120.
But sir, why 120? 180 minus 30 is 150, na sir?
I think this one.
So we have to consider theta with respect to major principal stress. So we will get 60 degree with major principal stress. When we put in the question 2 thetas, then it will be definitely to 120, sir. 2 into 60.
Sir, in that formula we use the theta corresponding to the major principal plane only.
Yeah. So but here in that case the theta 30 is okay. But in this case, how do you determine the theta? See, suppose this is the major and this 30 is perfectly alright. In that case, then we will get the failure plane here.
Sir, here 30 degree is made with horizontal, which is the minor principal stress plane. So when we minus 90 minus 30, that will be 60 degree with 50 stress. That is major principal plane, sir.
Sir, the pole will be on sigma 3, no, sir, I think.
No, 4 will be at the sigma 1 only. Because this is the major, minor, the lateral direction is the major principal strain.
Yes.
Sir, that theta will be 60
sir-
degree, sir. I was telling about 2 theta. 2 theta will be 120 degree. Theta will be 60 degree. In
Okay. Just check it once.
Yes. Bye.
And sir, here the sigma and formula, sigma 1 plus sigma 3 divided by 2 minus sigma 1 minus sigma 3 by 2. Where the given formula that you have written on board, that will be considering all the forces, means all the stresses are tensile, that means positive tensile, sir.
That is immaterial. This is a generalized formula. Okay, this is generalized formula. Now, whether you take sigma 1 as a positive or negative depending upon the stresses that you consider. Suppose here in this case compression is a positive, you are giving input sigma 1 as a plus 20. Suppose if it is a negative, then you directly insert minus 20. Okay. Equations will not change.
Sir, here 30 degree we are taking from the minor principal axis. When we take it from the major, it will be 60 and the answer will be same, sir.
Okay, very good. So if you take with respect to the major principal stress, it will be 60, not 30. So 90 minus 30, that is 60. So then you will get the same answer.
No, sir, it will not getting same answer, sir. When we put in formula, sir, then we will get 47.5, sir.
Others, can you please check it?
So sigma 150 plus 20 divided by 2 is 35, and plus 50 minus 20 is 30 divided by 250 cos 120, and cos 120 when we find, sir, Okay, sir. Let me check, sir.
So sigma n value 27.5, sir. But tau n is 12.99, sir. When we substitute theta equals to 60.
But not minus 13, sir. This is a positive 13. Tau and value, sir.
Ah. So you should get negative 13, not positive 13.
Sir, this is the problem with this formula. We have to check at every time we have to check with the theta. It is coming
Right.
correct or not.
Yeah, that is true. That is true. That's why the graphical way is the better. But anyway, so this problem I have given you just to avoid all this.
Sir, I'm still confused. Why pole in theta 1, sir?
See, where is the major principal axis and where is the minor principal axis? Your pole is always corresponding to the major principal axis.
Okay, sir.
So here the major is in the vertical plane. So that's why the pole will be at the sigma 1, not at the sigma 2.
And sir, actually, sir, formula is tau n equal to minus sigma 1 minus sigma 3 divided by 2, sir. There will be minus in, sir, coefficient, sir. Sir, I have derived formula also, sir.
No. See, you are saying this one
No,
is
no, sir, in
minus.
sigma, tau n, sir.
Sigma
Tau
1
n.
sigma 3 by 2, na?
Yes, sir. It is correct, but only things is we have to add minus 1.
Where?
Means, sir, we have to minus add a coefficient, sir.
No. That depends
Sir,
upon
it will be sigma 2 minus sigma 1 by 2. He's telling that.
No, sir. Means like a sigma 3 minus sigma 1 divided by 2. That will be.
See.
So when we use analytical formula for this tau, we get positive to value like 13 value. But from the graphical, we get minus 13.
Yeah, graphical it is correct. That positive you are getting because so you are taking the theta with respect again as a minor principal axis. The moment you take it with respect to major principal axis, your
So no, sir, I took theta as 60. That is with the major principal plane.
sin 60,
Sine
Sin
120.
120, sir.
sin 120 you take it.
Yes, sir.
Sir, when we'll derive the formula, sir, then we will get sigma 3 minus sigma 1 divided by 2 sine 2 theta, not sigma 1 minus sigma 3 divided by 2 sine theta, sine 2 theta.
That you don't get confused.
So I think we should move ahead now. We'll check it later.
Yeah, you will check it later. Okay, go to the next sum. Okay, so next sum is also quite easy. So determine the shear strength in terms of the effective stress on a plane. So within a saturated soil mass at a point where the total normal stress is 200 kilopascals and the pore water pressure is 80 kilopascal. The effective stress shear strength parameters for the soil are C dash 16 kPa and pi dash 30. So determine shear strength in terms of the effective stress. So what is the equation for the tau? So tau is equals to, in terms of the effective strength,
C plus sigma 10. C bar plus sigma 10. Sigma bar 10.
dash tan
Pi dash.
dash. So C dash has been given, pi dash has been given. Or what about sigma dash?
Sigma minus C.
Yeah. So this is C dash plus sigma minus u into so tan pi dash. So substitute everything. What you will get is the effective shear strength of a soil.
Sir, this is third question, sir.
This is third question. Okay, so it doesn't require much explanation. Now let us move to the fourth question. This is the most important question, the fourth one. So everyone read 1 or 2 times very carefully. So a saturated clay sample was obtained from the field without allowing the water content and the void ratio to change. The sample was subjected to the following stresses in the field. Sigma is equals to 240 kilonewton per square meter, U is equals to 140 kilonewton per square meter, sigma dash is equals to 100 kilonewton per square meter. And here points A to H, so you have been asked to calculate what are the different stresses acting on it. Now first, let us try to understand what has been given in the sum.
Sir, this is a third question, na sir?
Pardon me?
This is the third question in our tutorial.
I think fourth question, na?
In tutorial, that is third question, sir.
Acha, okay. Let's see.
And so previous question I didn't find, sir.
Okay, then leave it. Maybe it's a very simple question, I might not have given. A saturated clay sample was obtained from the field. So this you could able to find it, na?
Yes, sir. The third question.
Yeah, okay. Now, let us try to understand what has been given. So when the sample is in the ground, so this was subjected to a total stress of 240 kilopascal, and the pore water pressure of 140 kilopascals, and the effective stress of 100 kilopascals. Okay, so this is the initial condition. So this is the initial condition. Now suppose if I bring the sample to the laboratory, what will happen to these stresses?
So 0, 0.
So first of all, the axial and normal stresses that will act are 0. And what would happen to the pore water pressure?
Negative pore water pressure.
Negative pore water pressure. And how much is the value?
Minus 140 kilopascal.
Okay. So, but before that, you have to read the statement of the sum once. What has been given the condition? A saturated clay sample was obtained from the field without allowing the water content and the void ratio to change. If I don't change water content and void ratio, so what is its implication? What is its implication? No change in water content and no change in water void ratio. What does that mean?
The U will be same as the ground condition.
No change in effective stress. No change in effective stress. No change in water content. No change in void ratio means no change in volume. Okay, so no change in volume means your sigma dash is retained as it is. So what was the initial sigma dash? 100 kilopascals. So the same 100 kilopascals is retained as it is. All right. So now what will happen to the pore water pressure?
Minus 100. Minus 100 kilopascal.
So minus 100. Sigma minus sigma dash. So 0 minus 100. So this is minus 100 kilopascals. Minus or plus? Sigma dash.
Minus, sir.
Sigma dash is equal to sigma minus u na. So U is equals to, yeah, okay. So minus 100 kilopascals. So the moment you bring the laboratory, the moment you bring the soil samples to the laboratory, so this is how the stresses will act. Okay, you need to understand very carefully. So what are the changes that is happening? Now, what is the third statement here? This is one. On sampling, what are the stresses acting on it? So these are the stresses that are acting on it. The total stress is 0. Effective stress remain as it is, and the pore water pressure will change. So that will become the effective stress will become the pore water pressure. So here the inherent assumption is that there was no change in the water content, no change in the void ratio, therefore there was no change in the volume. Okay, but in the field, so measuring the total stress is very difficult. So always here, fortunately, it has been given sigma dash of 100 kilopascals. So most of the time, what we know is only the total stress and pore water pressure. So remaining things we should able to calculate. Now, from this state, what has been done? The sample was placed in a triaxial cell and was subjected to a cell pressure of 100 kilopascals under undrained condition. Under undrained condition. Now let us come to the P point. So now this was consolidated. This was consolidated with a pressure of 100 kilopascals. Is it okay? So this is in the triaxial setup now. So the sample was placed in a triaxial cell and was subjected to a cell pressure of 100 kilopascals under undrained condition. Under undrained condition. So now what is the meaning of undrained condition?
Water is not escaped during the load.
Okay, so no water is going out from the soil sample. So what does that mean?
Pore water
Pressure develops.
remains unchanged.
Yes, there is a possibility of the development of the pore water pressure. Okay, now here the sigma is 100. Sigma is 100 kilopascals. Okay, so now what will happen to the pore water pressure? Since the soil is undrained condition, whatever the cell pressure that you are applying will be taken by the soil itself, because this is a fully saturated. See the statement also. This is saturated clay sample. So therefore all the load will be borne by the soil sample. But initially the pore pressure of minus 100 exists. So minus 100, then additionally 100 in the form of a cell pressure is applied. So now the effective the net pore pressure will become 0. The net pore pressure will become 0. So then what will happen to the sigma dash? So sigma minus u. So your total will become now effective. So total will become now effective stress. Now go to the third point. The cell pressure was raised to 320 kilopascals with the drainage valve closed. So the cell pressure was raised to 320 kilopascals. So this is 320 uniform, that is isotropic loading condition. But here, what is the condition? So drainage valve is open. Now, what is the first implication of drainage valve open?
Consolidation will occur.
Consolidation will occur. Consequently,
The water gets drained. The PWP gets drained.
yeah. So the moment you see that the drainage is allowed, you should immediately put U as a 0. Pore pressure is 0. That's what now. whenever you see that the valve is open, there is no development of the pore water pressure. Even before you are understanding about total and effective stresses, you should straight away put U as a 0. U as a 0. Now what will become your sigma total and sigma dash?
320, 320.
Sir, I'm not getting U equal to minus 100 plus 100, sir.
But just check it.
I didn't see it is a drainage valve closed, I think.
Yeah, drainage valve closed. Yeah, correct. Yeah, what is your question? See, initially here in the when you brought the sample to the laboratory, so the pore pressure within the soil sample is 100 kilopascal. Okay, Vishal.
Yes, sir.
Now, on this or against this 100 kilopascals of the pore pressure, you are applying the cell pressure of 100 kilopascals.
So, sir, all cell pressure are converted into pore water pressure.
How? It's not converted. See, already there is an internal pressure of 100 kilopascals exist, but externally you are applying the 100 kilopascals. So therefore, the internal pressure will try to compensate the external pressure. Meaning thereby this indicates that the entire load is borne by the water only. So the negative pressure is becoming now or moving towards the positive. Here fortunately it is 0. Suppose if I say 120 kilopascals, then the net pore pressure will be positive 20 kilopascals. Initially it is negative 100 kilopascals, but here it is 0. Or suppose say if I take 120, and this will become positive 20 kilopascals.
Sir, you have applied, sir, 100 kilopascal as a cell pressure, sir. So
Yes.
how can we add, sir, in pore water pressure? Sir,
It's not adding. See, what is the drainage condition?
close, sir.
When the closed, the pore water pressure develops or dissipates.
Sir, develop.
Where is the development is taking place?
Sir, what?
See, the pore pressure is developing now.
Yes,
Okay.
sir.
You take here 10 kilopascals is applied. Now what would be the pore water pressure here?
Minus 90, sir.
Minus 90 is increment or decrement?
Sir, increment by 10 kilopascal.
Okay. So now suppose if I increase to 50, it is
Yes, sir, minus 50.
Vishal,
Yes, sir.
is it okay? If I apply 50, it will become minus 50. And as you keep increasing up to 100, where the internal pore pressure will become to the external applied cell pressure. That's what is the meaning of U is equals to 0.
Okay, sir.
Okay. Yeah. So let us go to the third condition. So here still the drainage valve is closed. Sorry, drainage valve is closed. Now the cell pressure is increased from 100 kilopascals to 320. So this is 100. So this is 100. So now what will become the sigma? What is the value of the sigma now?
320 kPa.
So 320 kilopascals. And what about the pore water pressure?
220 kPa.
So here 320. So already 100 is compensated. Already 100 is compensated. So you have increased effectively from 100 to 320. You have increased the cell pressure from 100 to 320. That means net increment is 220 kilopascals. Since the drainage valve is closed, so the entire load is borne by the pore pressure. So therefore, so this will become, so initially 100, so 320 minus 100, that is 220 kilopascals. 220 kilopascals. Then your sigma dash is equals to, so 320 minus 220, so this will become 100 kilopascals. Okay, so I will stop it here. So maybe in the day after tomorrow's class, Thursday class, so we can able to complete this one. But in the meantime, if we can able to finish it up, able to solve the remaining problems, that will be quite good.